Good morning, learners. In this video, we are going to look at the Euclidean geometry questions of the November 2015 paper. So question 8, 9, 10, 11. Question 8 is just a proof. We can quickly look at that as well. In the diagram below, cyclic quadrilateral ABCD is drawn on the circle with a center at O. Complete the following statement. The angle subtended by a chord at the center of a circle is what? The angle subtended by the same chord at the circumference of the circle. So this is the angle at the center is twice the angle or double the angle at the circumference. That theorem that I just wanted you to complete. So you can just say twice or double. And then 8.1.2 is used in question 8.1.1 to prove that A plus C is 180. A plus C is 180. The opposite angles of a cyclic quad are supplementary. They want you to prove that theorem. Normally you have to construct these two lines. They already did that, so I'm just going to start off to the construction. So using this theorem, the angle at the center O1 is double the angle at the circumference A. O1 is double A. That's angle at center is 2 times the angle at the circumference. And then in the same way, O2 is double C, angle at the center equals 2 times the angle at the circumference, and then since O1 and 2 together, there is a revolution. O1 and 2 together is 360 degrees. The reason there is angles round a point. Angles round a point is 360 degrees. And then O1 and 2 together is then also 2A and 2C, which is O1 and O2, O1 and O2 is 2A and 2C, is then the same thing, is 360. And then if I divide by 2 every single term, I have that A plus C equals 180. And that's what I wanted to prove here. Alright, so that's question 8. It's an examinable proof. Question 8.2 says, in the diagram below, CD is a common chord of the two circles. So CD is a chord that lies in this circle, but also in that circle. Straight lines ADE and BCF. ADE and BCF are drawn. Chords AB and EF. AB and EF are drawn. Prove that EF is parallel to AB. So I want to prove that EF, that line there, is parallel to AB, that line there. Now, to prove lines are parallel, I must use alternate angles or co-interior angles or corresponding angles. So I want to use that to prove that the theorem is true, because normally if this is parallel lines, then that angle A plus that angle E would be 180. Now, conversely, if I can show that A and E in some other way by not using parallel lines, if I can show that A and E together is 180, then the lines would be parallel because co-interior angles holds up. So I can maybe try that. Now I know that A is equal to C2 by it's an exterior angle. This is a cyclic quad and that line is extended. So C2 there is the exterior angle of the cyclic quad, which is equal to the opposite interior. So this one is equal to that one, but this one plus this one is 180. So if this one and that one is equal, this one plus this one is 180, also that one plus one, that one will be 180. So I can start by saying off that A is equal to C2. A is equal to C2. That's exterior angle of cyclic quad. cyclic quad, and then I can say, but C2 plus E is 180. They are opposite angles of a cyclic quad. So I mainly have these two theorems with cyclic quads, that the exterior angle is equal to the opposite interior, and the two opposite angles are 180 together. So I can use that now. If C2 is A, I can replace the C2 here with A plus E is 180. And then if A plus E is 180, if you look at the sketch, A plus E is 180, those are co-interior angles of those lines. So then I can say that AB and EF are parallel. AB and EF are parallel. So I can say that because the co-interior angles are supplementary, I can use converse of co-interior angles. Okay, normally if the lines are parallel, I would say A plus E is 180, and then my reason is co-interior angles. Now I'm using the backwards of that. So since the co-interior angles are 180 or supplementary, then the lines would be parallel. So then it's converse of, because I'm using the theorem backwards. Okay, so that's 8.2. We can move to question 9 then. In the diagram below, ABC is drawn in a circle. ABC, this is a triangle drawn in a circle. TA and TB are tangents, those. Now I have a theorem that says that tangents from a common point are equal. So I can somehow mark that in there. Or tangents to the circle, the straight line THK, straight line, is parallel to AC. So that's parallel, meaning that angle K2 will be equal to the angle A1. For instance, those are, then if this is parallel lines, those are alternate angles, and these are corresponding angles. So those will be equal. Just to mark some of the information that they give to me there. Parallel with H on BA, H is on BA, I see that, and K on BC, K lies on BC, AK is drawn, that's that line AK, let A3 be X, so this line there is X. Okay, prove that K3 is also equal to X, that angle there. Now I can see that angle is equal, I already marked that to that. Is there any way that you can see that this angle is equal to that one? Yes, because that's a tangent. This is a chord, and the angle between a tangent and a chord is equal to the angle formed on that chord in the alternate segment, tan chord theorem. So x, that A3 will be equal to C, tan chord theorem, and then C will be equal to K3 by corresponding angles. And that's what I need to prove there, that this is equal to that. So I can just write that down. A3 is equal to C. That was tan chord theorem. Tan chord theorem. But C is equal to K3 by corresponding angles. And in this question, there's only the one set of parallel lines, but TKAC. So it's not really necessary to list the parallel lines there, because there's only the one pair. But if there's more than one set of parallel lines in a sketch, it's always just considerate to the person marking to just name the set of parallel lines, so that they can clearly see where were you looking and what are you doing there. Okay, so 9.1, then A3 is K3, and I have the information that A3 is X, so that means then obviously that K3 is X. And from this, it's also useful to know now K3, C, and A3 has now been all established as X and X and X. Okay, prove that AKBT is a cyclic quadrilateral. Prove that AKBT AKBT, this one here is a cyclic quad. Now to prove a cyclic quad, you can do one of three things. You're going to use converse of, and you want to show that some properties of a cyclic quad is valid here. So I'm looking for an exterior angle that's equal to an opposite interior of this quadrilateral, because that's a property of a cyclic quad. So maybe if I can show that K1 is equal to T1 and 2 together, if I can show that somehow by not using that it is a cyclic quad, because I want to show that this is a cyclic quad. So I can't use the fact that this is a cyclic quad, I must show it. So if I can maybe show that this angle here is equal to that, then the exterior angle of this quadrilateral is equal to the opposite interior, and that's then a valid argument for this to be a cyclic quad. Or alternatively, I can look for opposite angles to be supplementary. So if I can show that B1 and 2 is plus A2 and 3 is 180, or that K2 and 3 is plus T1 and 2, this is 180. If I can show that somehow by not using the fact that this is a cyclic quad, then this would be a cyclic quad. Or I can look for that angles in the same segment theorem. So from chord, if I look at this as a chord AK, the angle formed on the circumference, if this does go through a circle, that angle B1 must be equal to that angle T1. So any of those. Now I already see here on the chord BT, that angle is X and that angle is X. So angles in the same segment is already equal here, meaning that this is a property of a cyclic quad. It holds up, making this a cyclic quad. So I can just say, actually here, 9.2, that A3 is equal to K3. I've already shown that in 9.1, so I don't need to make an argument for it again. A3 is equal to K3 in 9.1. But then AKBT is a cyclic quad. Since the angles in the same segment are equal. Now, since again I'm using this theorem backward, normally if it is a cyclic quad, then the angles in the same segment will be equal. That's the theorem. So what I'm doing now is I'm saying the angles in the same segment are equal, thus going back it must be a cyclic quad. So I'm using converse of, using the theorem backwards, converse of angles in the same segment. Right, okay, that's 9.2. 9.3 says now prove that TK bisects AKB. So the angle AKB is this angle K2 and 3 there. And if I want to prove that TK, this line here, bisects that angle, bisects means cut in half, by 2, sect, cut. So cut in 2 exactly in half. I basically want to show that K2 and K3 is equal to one another. Right, now already I have that is equal to X, so I'm looking for some reason why this one is equal to X. And you can also use information from the questions above. So since I immediately think, oh, but I proved this is a cyclic quad, so this angle here will be equal to that angle there. I also said it will be equal to this angle, but neither of those are X. I'm trying to look at why this is X. So this one is equal to that one, but, oh, you see this? This one will also be equal to that one, which is X. So there's my root to show that this is X. This is X already. I want to show that this one and this one is equal. So I basically want to show this one is X. So K2 is equal to B2. They are angles in the same segment in this cyclic quad that I've just proven to be a cyclic quad in the previous question. And then this angle B2 is equal to A3, because it's an isosceles triangle from the tangents being equal. Okay, so, but now to write that down. So I'm going to start off by saying K2 is B2. K2 is B2 because it's angles in the same segment. And since I'm now here working with a bit of a controversial cyclic quad, I'm just going to also say angles in the same segment in A, K, B, T, which I just proved to be a cyclic quad. So I'm just mentioning that also for the person marking my work so that they can see what I'm doing there. And then, but B2 is also equal to A3. And there's actually two reasons involved here. It's because those lines are equal. I haven't stated that. The lines are equal because of tangents from a common point. You can write tans from a common point. That's tangents from a common point. The lines are equal, but then also if the lines are equal, then the angles will be equal underneath that because they are angles opposite equal sides. But I must first just state that the sides are equal because it wasn't given to me. I know they're equal because they are tangents from the same point. So you must just state both the reasons. Don't write isosceles as a reason. This is the reason for isosceles triangles. The angles opposite equal sides of the triangle are equal to one another. Okay, then 9 point. So, I must just make my argument clear. So I've shown here that that K2 is x now because all of these angles are x actually. I'm just going to say, okay, so K2 is x and K3 is also x because I've shown that in 9.1, and that means then that K2 is equal to K3. Just to make the argument clear, I've shown that the line bisects the angle, so the two parts of the angle are equal. I want to show that this line bisects this angle, so K2 and 3 must be equal, just to make the argument clear there. And then 9.4, prove that TA is a tangent to the circle passing through points AK and H. Prove that TA, this line here, is a tangent to the circle passing through AK and H. Now, if that's a tangent and there's a new circle going through there somewhere, I'm supposing it will probably go a bit like that. Basically, I want to show that if there's a circle going through AK and H, this must be a chord of that circle. So I want to show that the angle between the tangent and the chord is equal to the angle formed on that chord. I want to show that A3 is equal to K2. But since this is x and I showed this is x just in the previous question, it's already done. So I can just write down the argument that A3 is equal to K2. I've actually already shown that there. You see 9.3. And since that is equal, I can say that then TA is a tangent to AKH, and then my reason for that is converse of tan chord theorem. I'm using converse when I go back. So if, let me just sketch here somewhere quickly. If this is 3 points lying on a circle and there's a tangent going, this angle will be equal to that one. So if this lies on a circle and that is a tangent, these two angles will be equal. Nope, I'm sorry. These two angles will be equal. The angle between the tangent and the chord, and then the angle formed on the chord, that one. These two will be equal. So what I've done in this question is I've shown that there's no circle and it's not information that is actually a tangent, but in a sketch that looks like this without the circle and the tangent, I've shown that that angle is equal to that one. The A3 is equal to the K2. that means that this is a tangent to the circle going through these 3 points, because it's a property of a tangent and a circle. So I'm using it backwards, then I use converse of. Okay, that's 9.4. Let's look at 9.5. Okay, right, question 9.5 says S is a point, there is S, okay. S is a point in the circle such that points A, S, K, and B are concyclic. A, S, K, B are concyclic. So A, S, K, and B lies on the same circle. It's given information to me that A, S, K, B lies on the same circle. Concyclic means they lie on the same circle. Explain why A, S, B, T are also concyclic. So I want to know why A, S, B, T are concyclic, right? Now, if it's given that these 4 points lie on the same circle, and previously I've shown that these 4 points lie on the same circle as well, sorry, that actually means that all 5 of these points lie on the same circle. So if ASKB lies on the same circle, ASKB are concyclic, they lie on the same circle, and also AKBT are concyclic, because I've shown that as a cyclic quad from question 9.2. That means that A, K, S, B, T, all of these 5 points lie on the same circle. Because A, K, B, there's a circle going through these 3 points. And on these 3 points, the information that A, S, K, B, there's a circle going through these 3 points, right? So the information that A, S, K, B or concyclic means that this point also lies on that circle, right, going through these 3 points. And the information from 9.2 that says this is a cyclic quad means this point also go through that same circle. There's only one circle you can draw through 3 points. So since I have the 3 points that are concyclic and this point lies on that same circle, this point lies on that same circle, that means that all 5 these points lies on the same circle. So then explain why ASBT will also be concyclic, because ASK B, T lie on the same circle. Right, then obviously A, S, B, T are concyclic. Okay, bit of a weird question there. It's good to know that you need at least 3 points to establish a circle. 2 points, when there's 2 points, you can still draw various circles through the 2 points. Like if I have 2 points there, I can draw a circle there, but I can also draw a circle there. I can also draw a circle. Nope, that one's not going to go through there. But I can draw various points, various circles through 2 points. But the moment I have 3 points, there's always only one circle that can go through all 3 points. I can't move this circle to other points. So the fact that A, K, and B is there and a circle lies with S makes this one circle, and with T also same circle, because there's 3 points going through that circle already, means that can only be the one circle, and all 5 points lie on that circle. Okay, question 10. We are moving into the grade 12 trigonometry here a little bit now. In the diagram below, BC, there is 17 units where BC is the diameter of a circle. Now, if this is the diameter of a circle, I know of diameters that, angles that are formed on them. Angle in a semicircle is 90 degrees. So I can swim mark that. Just take a sip of coffee, sorry. Okay, so BC is the diameter. The length of chord BD is 8 units. The tangent B, so there's a tangent. And I also know of tangents and diameters that they are also perpendicular. If I know my theorems very well, it makes my life a lot easier with some of these questions. The tangent at B meets CD produced at A. Produced just means made longer. So CD produced, this tangent meets it there at A. Okay, calculate with reasons the length of DC. Now I have that 17, I have this 8, this is a 90 degree. So I can use Pythagoras to calculate DC. But before I use Pythagoras, I must just state that that is a right angled triangle. So BDC 10.1. BDC is 90 degrees because it's an angle in a semicircle. And then I can use Pythagoras. So DC squared is equal to 17 squared minus 8 squared. I'm going to need my calculator, which I don't have here next to me now. So I'm just going to use a calculator on my phone quickly. 17 squared minus 8 squared is 225. And then when I take the square root of that, DC is 15. Units, centimeters, units. Okay, the question is not talking about centimeters, so then I don't work in centimeters. So DC is 15 units. Calculate the length of DC, 15 units. There we go. I used Pythagoras here. When you are working with Euclidean geometry, quite important that you always give your reasons. In other sections like trigonometry, not always that important. If you forget the reasons there, it's fine. But in Euclidean, you must be very precise. 10.2.1. E is a point on BC. BC, E is a point on BC, such that BE to EC is a ratio 3 to 1. BE to EC is a ratio 3 to 1. So I can make BE 3K and EC 1K. The K just means it's not 3 units and 1 unit. That would make this 4 units where I can see clearly it's 17. But 3 parts of the 17 is here and 1 part of the 17 is that length. So basically if I divide the 17 into 4 parts, because there's 3 and 1, 3 of that 4 parts, or 3/4 of 17 would be this length and 1/4. Okay, right. EF is parallel to BD, that's great. With F on DC, calculate with reasons the length of CF. So I can see here by the parallel lines the proportion theorem. The proportion theorem says that the proportion of these two sides will be the same as the proportion of those two sides. So I can say here that DF to FC, and you can write this like this, DF to FC is a ratio 3 to 1, same as on the other side, because of the proportion theorem, prop theorem. And with prop theorem, always please list EF, BD, your parallel lines that you're looking at, okay? Or you can write it like this, or you can write it like this, DF to FC as a fraction is 3/1. So you can write it like that. Same thing, it means exactly the same thing. Okay. And I want to calculate the length of FC. So this basically tells me that FC, that part, which is one of the 4, you see there's 4 parts DF to FC is also a ratio 3K to 1K. And you can see this is one of the 4 parts of the length of DC. So this is a quarter, and that's 3/4 of the length of DC, which DC I calculated to be 15 in the previous question. So to calculate the length of CF, I can literally just say CF is 1/4 of the length of DC, which is 15, and that I can use my calculator again for. I wonder if I should not maybe quickly check where my calculator is, but I mean, this is fine. Look at this cool calculator app, my script calculator that I have on my phone. So I want to calculate 1/4 of 15, and that's 3.75. Is that not cool? Okay. It's an app you can download from the App Store, and it actually can work out logs and sine and cos and tan and fractions, and yeah, it's quite an interesting app. Okay, 10.2.1, calculate with reasons the length of CF is then 3.75 units. Now question 10.2.2 says prove that triangle BAC is similar to triangle FEC. BAC, it's the big triangle here in the sketch, the biggest triangle there, is FEC, the small one there, FEC. So to prove similarity, what I want to do is I want to show that the angles here are equal, the sets of angles. So I'm looking for an angle in this triangle that's equal to an angle in that triangle. Now, since C lies in both triangles, I have that angle C is equal to angle C. It's a common angle. Common angle. Okay. With the similarity proofs, let me just mention this. It's important that you have all of the angles from one triangle on this side and all of the angles from the other triangle on this side, just to make your listing here easier in the bottom. So I'm going to list the small triangle on the left hand side and the big triangle on the right hand side. Just take note of that. Okay, so then I'm looking for any other angle here. Now I see this one here, since that is 90 and these are parallel lines, this one here will be 90 as well. So angle EFC on the small triangle, EFC is 90 by its now I'm spacing out on that word. You know what that word is. I used it earlier in one of these questions. Corresponding angles. Oh my word. Sorry about that. Corresponding angles. Corresponding angles. Okay. And my parallel lines EF and BD. EF and BD. Okay, so EFC is 90, that's corresponding angles. And also in the big triangle, that angle is 90. I haven't stated why yet, so I must still do that. EFC is 90, and 90 is also equal to ABC. And you take note, 90 is also equal to ABC because a tangent is perpendicular to a diameter. Take note how I keep the small triangle angle on this side and the big triangle angle on this side, because I'm listing my small triangle angles on this side and bigger triangle on this side. Take note how I didn't write ABC as 90. I just wrote is equal to 90 because I'm trying to keep the bigger triangle on this side. And then the third angle in this small triangle is that angle FEC. So angle FEC should then be equal to BAC. BAC. You don't actually need to go search for a valid reason. In any two triangles, if two angles are equal, the third angle of the triangles will by default be equal because of the sums of angles in a triangle. Since C plus F plus this is 180, and C plus B plus this is 180, and these are equal. The third one should be equal. If you have 20 plus 70 plus X, which is then 180, and 20 plus 70 plus X is 180, plus Y, the X and the Y should obviously be equal to one another. Okay, so then to list here, you see now my listing from here. So triangle, and I look at the angles CFE. CFE is similar to triangle CBA. CBA. Angle. You see why I list this, the one triangle and the other triangle, then I don't actually even have to go look at the sketch. I can just see from here CFE, CBA in the same order, right? Because this order should be correct, because from there the similarity proportions are just easier to write down if this is in the correct order. If you listed EFC is similar to ABC, that's fine, but you can't swap these letters around and keep this the same. This must be in the same order. So in the two triangles, the C is equal to the C, the F is equal to the B, you see, and the E is equal to the A. The E is equal to the A. Good. Okay, so that is then my similarity proof, and then calculate the length of AC. So I want to use the similarity now here. So quickly look at this, 10.2.3, to calculate the length of AC. You see now, to write down my similarity, I can use CF over CB. CF over CB, whatever I take on this side, I take the same on that side, is equal to FE over BA. FE over BA is equal to CE over CA. CE over, and I'm not going to write CA, I'm just going to write AC and AB and EF. I actually should do that. CF over BC is equal to EF over AB is equal to CE over AC. Okay, all that I did now from there to there, it's the same side lengths. I just also wrote them in alphabetical order rather. So I don't want CF is fine. I don't want CB because B comes before C. So I'd rather write it as BC. So I wrote the same thing down just in alphabetical order everywhere. I suppose that does not really make such a big difference. It's not really a bad thing, but meticulousness is really your friend while you are doing Euclidean geometry. So just to show you again where I got from there to there, I took CF over CB. You see at the same place, CF over CB, CF over CB or BC is equal to FE over BA, FEEF over AB, BIAB, same thing, is equal to CE over CA is equal to CE over CA or AC, right? From similarity, and now I want to work out the length of AC. So obviously I'm going to work with this AC and CE, which is 1K. I can easily get the length there. It's 1/4 of 17. And the other ones that I have here, I only need 2. I wrote down all 3. I'm obviously going to need this one because I need the length of AC, right? But I only need one of these. I'm just going to check the sketch to determine which one is a better one to use. Obviously one where I have information. So CFBC, CF BC, you see I have those lengths. That's a good one to work with. CF and BC, good one to work with. EF, AB, I don't have that. EF, I don't have that. Not a good one to work with, right? I can probably get those lengths, but it's going to take me some time, where these ones I already have the lengths. So I'm just going to work with those two. Alright, so CF on the sketch is that 1/4 of 15, 3.75 units that I already calculated. CF 3.75 units, so CF is 3.75 units. BC is 17 units, it's given to me on the sketch. BC 17 units is equal to CE. I'm going to need the value of CE, which is 1/4 of 17. CE is 1/4 of 17. Which is then 4.25. 4.25. So CE is 4.25 over AC, and then from this I can just cross multiply. So 3.75 times AC is 17 times 4.25. So AC is the 17 times 4.25 divided by this 3.75. 17 times 4.25 over 3.75, and that is 19.266, which can round to 19.27. Okay, all right, so that's the length of AC. And then the last question here in 10 is 10.2.4. Write down, giving reasons, the radius of the circle passing through points A, B, and C. So through points A, B, and C, the radius of the circle. Now, if I look at this A, B, C, since that is a 90 degrees, I can immediately assume that AC is going to be the diameter, so the radius is just going to be half of AC. So since 10.2.4, since B is 90 degrees, I already stated that earlier, AC is the diameter. The reason what I'm using here is the converse of angle in semicircle. Converse of angle in semicircle. And then if AC is 19.27, then the diameter is 19.27. The radius is going to be half of that. So I'm just going to take this half of that. It's going to be 9.63. 9.63 units. Okay. Alright, and that's question 10. Last question in this question paper on Euclidean is going to be the question 11. Right. Complete the following statement. Okay. If the sides of two triangles are in the same proportion, then the triangles are similar. Similar triangles have sides that are in the same proportion. Okay, 11.2. In the diagram below, K, M, N respectively are points on PQ, PR, QR, of triangle PQR. KP is 1.5, PM is 2, KM is 2.5, MN is 1, MR 1.25, and NR 0.75. So they give me all of this information. It's also on the sketch. Prove that triangle KPM, this triangle there, is similar to RNM, RNM. Now, normally, to prove similarity, I would look for equal angles, but since I can't really see any reasons why any angles here would be equal for that matter. And they helped me a little bit with if the sides are in the same proportion, the triangles are similar as well. So there's something else I can look for. So let's look at this. 1 over 2 is a half, 1,25 over 2,5 is a half, and 0,75 over 1,5 is a half. So the sides are all in the same proportion. So what I'm going to do is I'm going to say mn over pm is equal to 1 over 2. nr over pk, nr over pk, pk is equal to 0,75 over 1,5, which is also a half, and mr over km, mr over km is equal to 1,25 over 2,5, which is also a half. So I've shown that the ratio between the sets of side is a half, a half, a half, which means that mn over pm is equal to nr, it's all a half, is equal to nr over pk. I don't want to make a p, I want to make an r there, is equal to mr over km is equal to mr over km. Sides are all in the same ratio, half, and that means that triangle, I'm now going to work from this MNR. MNR is similar to triangle PMK. I think it should be MPK. MPK. I'm just going to check quickly. MN over MP is equal to NR over PK is equal to MR over KM. Yeah. Okay. Just check that holds up. So, or you can just write it like this, because they would not give it to you in the wrong order. So since they gave you the order there, you can work with that as well. Determine the length of NQ. Okay, so NQ is this here. So I think what I should do is maybe prove that this big triangle here is similar to one of the smaller triangle, and then work with the ratios from there. Since NQ and NR, it's maybe a good idea to work with this small triangle and the big triangle there. So let's do that. Okay, in this triangle and this triangle, the angle R would be equal because it's a common angle, and then I'm looking for this angle N would be equal to the angle P from similarity, right? So this angle N would be equal to the angle P from similarity in this triangle, and in this triangle those two will be equal, and in the small triangle and the big triangle both these angles are then, this is an angle of the small triangle and this is actually an angle of the big triangle as well. So these two are equal, then by default the angle M would be equal to the angle Q because it's the third angle. So there's my proof of similarity. 11.2.2. I'm going to say angle R is equal to angle R. It's a common angle. Then angle MNR. So I'm listing now here MNR is equal to angle P. I'm listing now the small triangle on the left hand side and the big triangle angles on the right hand side. Just take note of that. As I said earlier, it just makes my listing at the bottom easier and the conclusions from there easier if this is in the right order. So MNR in my small triangle is equal to P, and this is equal from similarity. Because you see that the N and the P lies in the same place. So angle M is equal to angle M, N is equal to P, R is equal to K from that similar triangles there. And then the third angle, NMR, that one in a small triangle on the left hand side, NMR is equal to the third triangle in the big one, PQR, that one there, PQR. It's just the third angles of the triangles, and then RNM, so I can say that RN triangle, RNM, you see I follow the what's equal, is similar to triangle RPQ. So even if there's other letters, I'm going to follow the angles here, RPQ. That's also why it's important to mark the angles, one of the reasons. Angle, angle, angle. And then from this, I can write down Rn over Rp. Rn over Rp is equal to Nm over Pq. Nm over Pq is equal to Rm over Rq. Rm over Rq. All right. From similarity. And then I'm trying to find the length of NQ, which is not here. NQ, oh, but sorry about that, NQ, but if I can find the length of RQ, that's great, because I can just subtract the 0.75. So I'm actually trying to find the length of RQ, which means I'm obviously going to work with this one, RQ and RM, and then I'm looking for something where I have information. RQ I need, RM I have the length, NM and PQ, NM and PQ, I don't have the length of, I have the length of NM, but I don't have the length of PQ. So let's look at that one, RN and RP. RN, I have the length, RP, I have the length, it's 2 and 1,25. So I'm rather going to work with these two. RN is 0,75, RN 0,75 over RP is 2 and 1,25, so 3,25. 3,25 is equal to RM. RM, which is 1,25 over RQ is the one, QR is the one that I want to calculate here, so QR. Okay, cross multiply there. I have 0,75 QR is equal to 3,25 times 1,25. 3,25, 1,25, and then to get the QR alone, I'm just going to divide the 0,75. So I have 3,25 times 1,25 over 0,75. 3.25 times 1.25 over, now it placed the 1.25, okay, over 0.75, and that's going to give me 5.416, what, and I actually want the length of NQ, which is then going to be the QR, which I have here now, subtract 0.75. So I also want to subtract 0.75 there, giving me 4.666, so 4.67 units. Okay, and that's the length of QN, and this is all the questions from the November 2015 paper. See you in the next one.